Deep in the constellation of Ursa Major, just off the tip of the Big Dipper, there lies a galaxy that is home to one of the strangest stars in the universe. This galaxy lies more than 500 million light years away from us, and is so obscure it doesn't even have a name yet. Regardless of this, one day in September of 2014, the Intermediate Palomar Transient Factory, IPTF for short, turned its camera to this patch of sky and captured a star going supernova. It was cataloged as such and given the designation IPTF 14HLS, which coincidentally is also the name of the next iPhone. It was recorded as a Type 2 supernova, meaning there were strong hydrogen lines in the spectrum, and it was predicted to dim in brightness after about 100 days. Only after close monitoring, it seemed that this star never stopped going supernova until more than 1,000 days later. This is really strange behavior for a dying star because the majority of supernovas are visible for about a month, with few stretching to the 100-day mark. But this one seemed not to care. It also varied in brightness a lot more than a typical supernova, having 5 peaks of significantly more light during that time. It has been just about a decade since we first detected this star collapsing and bouncing back into a supernova, and since then it has faded from our telescopes and is believed to have formed a remnant nebula with a neutron star or black hole at the center. So let's take a look at one of these graphs from a paper on this supernova in a little bit more detail. This is a paper by Sollerman and collaborators, and you can see this is a light curve of the supernova. The most interesting thing about this is obviously the length that it took the supernova to eventually fade away. And when reading this graph, we can see that there's different telescopes that these data was taken with, indicated by the different markers. And then also different band passes of the filters that were used. So this supernova was brightest in the infrared and darkest or less luminous in the blues. And you can see the apparent magnitude and absolute magnitude both marked on the y-axis here. And what's really weird about this supernova is how it goes up and down like a roller coaster. So we have at least 1, 2, 3, 4, maybe 5. The researchers say that there's 6 peaks. I can kind of only see 5, but that's my untrained eye. Which is really weird because you would expect a supernova to kind of go up in brightness and then fall off very rapidly instead of this kind of weird fluctuation, up and down motion that the light curve is doing. So here we have a bunch of spectrums of the supernova as a function of time. The time progresses going down. So you can see this is day 713 up here, and at the bottom we have day 1170. These are also taken with different telescopes and spectrometers, so we see slight differences in the actual wavelengths that they're able to capture, like this one from Keck 2 is quite a bit shorter and has a bit more error. But generally we're able to see the hydrogen alpha emission line for all spectrums that were taken, and what we can see is that the amplitude of these peaks doesn't really go down as a function of time, which is weird because in typical supernovae we see the hydrogen going down as it gets fused during the supernova collapse and then explosion. So this kind of is a very weird footprint of the supernova that isn't really typical of most. We're also able to see, looks like some iron down here that isn't really present at the beginning but is towards the end, which is interesting. But I'm also seeing other iron lines up here that are present at the beginning, so that's an interesting discrepancy. And it turns out that this observation in 2014 wasn't actually the first time that this supernova was observed. In 1954, they observed a supernova in the same location in the same host galaxy and believed that it was a precursor to the one observed just last decade. There are a lot of theories to predict this behavior, but none have really hit the nail on the head so far. Some of them include really strong stellar winds or the star burping in a way, the material falling back onto the star and causing multiple collapses and then subsequent supernova explosions. Theories also suggest that there could be a neutron star or magnetar companion to the star, which could cause some of these spectral features. And the last theory that I could find is one that proposes that there could be some sort of antimatter core in this star that could cause it to be weird, but we don't really know, and that's kind of the cool thing about this. Scientists are constantly doing research and learning more about the universe, and we may never know the case for this star, but hopefully what we learn from this star we can apply to future supernovae that may take a similar form.